Hi ladies, this is lesson 6.1. It's all about symmetry. And in this lesson, we're going to look at, or in this whole chapter, we're going to look at applying transformations. So this one is specifically about symmetry and transformations. So we're going to use what we've used before, rigid transformations. So they don't change shape and they don't change size. That's what rigid means. And we're going to use those to describe symmetry. So here's a list of vocab terms that you have on your note sheet, and we're going to define some of these vocab terms. Some of these you should already recognize, they should look familiar, but we're going to apply them specifically to this lesson, and we're working with polygons. So let's look at your note sheet, and before we define any of these, you have three visuals here. Which one of these, based on what you know about reflectional symmetry, which one of these has reflectional symmetry? This first one has reflectional symmetry. So reflectional symmetry, you can draw a line on the image, and that's just like holding out a mirror. So in this image, for example, I'll use a dotted line. But if I drew a line right down the middle here, and I reflected this left side over the line, I would get exactly what's on my right side. Could do the same thing if I drew a line right through the middle horizontally. Okay, the top, if I held out a mirror right on this line, the top would reflect in that mirror and it would coincide with that bottom image. So reflectional symmetry, as a definition, a figure has reflectional symmetry if a figure can be reflected over a line that the result coincides with the original image. And then that line of symmetry is the line of reflection. All right, now let's look at rotational symmetry. Again, we've worked with rotational symmetry before, but which one of these images has rotational symmetry? Well, if I copied any one of these images and I spun the image, so as I'm spinning it, how far do I have to go until it coincides with the original image? All right, so this was my starting point. This was at the top middle here, but now it's at the bottom middle. So this image has rotational symmetry. What about this next image? Is this the same? And this is a little different because it's a rectangle, but here the image is the same, and as I'm rotating it here, it's the same. Okay, so this second image also has rotational symmetry. Now this one, I copy this one and I rotate it. Even if I rotate it 180 degrees, it's not the same. It's very similar, but it's not the same until we get all the way back to the original. So this image does not have rotational symmetry. So rotational symmetry, as a definition, a figure has rotational symmetry if a figure can be rotated about a point such that the rotated image coincides with the original. So something to note about rotational symmetry is any figure is going to have rotational symmetry if you count 360 degrees as rotational symmetry, or any product of any multiple of 360 degrees. But really, when we're talking about rotational symmetry, we're talking about something that can be rotated less than 360 degrees, and it still coincides with the original image. So a point of symmetry follows this rule, has to be less than 360 degrees. So a point of symmetry is also known as twofold rotational symmetry. Okay, that means that it has to, between the rotation of 0 and 360 degrees, there has to be two symmetrical images. All right, and then let's look at our images again. And which one of these has translational symmetry? That would be this last one. So translational symmetry means that you can slide the image, and actually let's slide it like this. This is the same image, right? So as we're sliding, we're getting that same image. So translational symmetry is the result of sliding a design by the same translation vector. And then the last term, glide reflection. So we're going to look at our footprints example again. So with a glide reflection, you can combine translation with reflection. So in this one, as we translate it, so look at the top set of footprints right here. As we translate this, and actually maybe I should just copy that top set. So as I slide this image, now it has reflectional symmetry. So a glide reflection is combining a translation with a reflection. So I'm translating it, and then I'm reflecting it so that it coincides with part of the original. So these footprints have translational symmetry and glide symmetry, or glide reflection. So going back to your terms, glide reflection combines translation with reflection. All right, now if you look at your note sheets, you have this example with a square. So here's your square, and all of these lines indicate lines of reflection. So we say that a square has four-fold reflection symmetry. That means you could fold a square in 4 different places and have it all reflect onto part of the original image. Now the same is true with rotational symmetry. A square, you can rotate it at 4 different spots between 0 and 360 degrees, and you have 4 figures that coincide with the original image. So a square has 4-fold rotational symmetry. All right, so if you're doing this with us in class, then we are going to trace these regular polygons onto a sheet of trace paper or patty paper, and I want you to mark each starting point. So if you're doing this at home, wax paper works fine, or parchment paper, any of that would work fine. but trace the image and or trace each figure, and on your figure, mark a starting point, both on the figure and on your traced paper. Okay, so it doesn't matter which point you mark as your starting point, but mark a starting point. So what we're going to do is on our traced paper, we're going to rotate that traced paper around each of these polygons. So for example, I'm going to trace a triangle, and then I'm going to rotate that traced triangle around the triangle to see how many times my image coincides with my original figure. And we're going to do that for all of these polygons. And just to note, these are regular polygons, so it'll be different if you choose to use irregular polygons. But then on this table, we're going to fill out number of sides of the polygon, so triangle, square, pentagon, hexagon, heptagon, octagon, and we're going to see if we can come up with a conjecture. So how many rotational symmetries can we have? And then also, if we were to fold our paper, how many times can we fold it so that our traced paper coincides with itself? Has a line of, how many lines of reflection can we find? So please do that on your own. If you're doing this at home, pause the video while you do this, and then you can unpause for the solutions. All right, so now you should have already done this activity. So looking at this table, you should see that in a triangle, you have 3 reflected symmetries and also 3 rotational symmetries. For a square, we already looked at square back in this example. It has 4-fold reflectional symmetry and 4-fold rotational symmetry. So that is filled in for you. With a pentagon, you should have seen 5 reflected symmetries and 5 rotational symmetries. With a hexagon, you should have seen 6 rotational and 6 reflected. Heptagon, 7 reflected and 7 rotational. And octagon, you should have seen 8 reflected and 8 rotational. So what does that mean? Can we draw any conclusions? What would it mean for an n-gon? Probably that there's going to be n reflected symmetries and n rotational symmetries, however many sides there are. So looking at your next sheet, your next page, this conjecture that you have, a regular polygon of n sides has n reflectional symmetries, and a regular polygon of n sides has n rotational symmetries. So again, this is specifically regular polygons. So regular meaning all sides are the same length and all sides are the same degree. The second one, I might draw a rectangle. And I want to be careful not to draw a square, because with a rectangle, I'll have two lines of reflection. One here, it's not quite there, but one about here, and then another one here. But if I drew a square, I would have 4 lines of symmetry. Okay, because here my diagonals are not lines of symmetry. Yes, they divide the quadrilateral into 2 congruent triangles, but it's not a line of symmetry. You maybe also drew an isosceles trapezoid. That would work fine too. It would only have 2 lines of reflection. Right, and then the last one is a triangle that only has 1 line of symmetry. So I might draw an isosceles triangle, not an equilateral triangle though. If my triangle was equilateral, then I would have 3 lines of symmetry, but with just specifically an isosceles triangle, I only have 2, which I think this is. All right, so here, or sorry, I only have 1. Here is my 1 line of symmetry. Okay, this is not a line of symmetry. And this is not a line of symmetry. Okay, so I just have, with an isosceles triangle, 1 line of symmetry. All right, so please jot down any questions that you have on this lesson and come to class with those so that we can discuss them next time I see you. Thank you.